So now I would like to discuss what's really happening with the new generations of memory technology and what it really means for them to hit the so-called memory wall. If you look at the speed, the interface speed and the aggregate throughput, that is how many gigabytes per second you can move between the controller and an individual memory device, and you plot that over time, what you're going to see is that the growth in memory speed interfaces is exponential. That is, every few years the speed is doubling, and every time the speed doubles, that is generally going to be described as a new generation of DRAM. The throughput in gigabytes per second between the controller and an individual DRAM, there's a wide distribution there, with GDDR5 being at the top at about 28 gigabytes per second. DDR and LPDDR actually are very similar at about 4.5 gigabytes per second, and then flash interfaces come in at about 1 to 1.5 gigabytes per second. Now, if you look at this trend, you'll notice that for DDR and LPDDR, that line is actually starting to roll off. So what is the reason that these lines that are showing the increase in memory speed over time starting to roll off? The reason is that memory technology is hitting a wall. Every time there's a new generation of memory, every time there's a new generation of products, the demand for higher and higher throughput increases. And so if you were to look at what the throughput requirements were, say, over the last few years and project that into the future, you can see that obviously throughput is going to be the product of how many interface pins or balls you have in the device and what the interface speed is for each one of those pins. And so you can either go faster or you can go wider in order to achieve any given number of gigabytes per second between the controller and the memory. And over time, that expectation is increasing. Now, if you look at current technology and what it can achieve, you really start to run into some fundamental limits. In one case, driven by Maxwell's equations, and the other case driven by materials and fabrication processes. The limit on speed really exists because signal propagation physics start to dominate the interface design. So everyone's heard about signal integrity. As you go from lower to higher speed, signal integrity becomes a more significant issue. And so things like crosstalk, loss, reflections, those kinds of things just become much more difficult to manage as speed increases. On the other hand, if you try and go wider, you start to run into problems with how many signals, how many balls or bumps can you communicate between a controller and the DRAM. And right now the current maximum on that is about 512 bits. So if you look at, say, a graphics card, you might see a 500-bit interface between the GPU and all the GDDR memories in there. How would you increase that to 1,000? Using current technology, it's extremely challenging to do that. And so in order to get to the next generation of throughput, it's going to require a breakthrough in either how you achieve higher speeds or how you can get wider I/O, and in fact it'll probably require a breakthrough in both areas. And so this memory wall here, which is boxing in current technology both on the speed and the interface front, is demanding a revolution in signaling and in interface definition, interface width.